we have Jay, and he's going to talk about building Daft, Python and Rust, a better distributed query engine. Question mark or not?
No question mark. I think
no
it's better.
No question mark. It's a fact.
Yeah, thanks for the introduction. Yeah, so I guess this is the follow-on Rust talk from just now. I hope you all stuck around. But yeah, so maybe a quick introduction. My name is Jay. I'm a co-founder of a startup called Eventual Computing. We are the maintainers of Daft. You can find us at this URL, getdaft.io. It's a data frame library, very similar to Polars. I'll show you all a little bit of a demo later. But yeah, prior to Eventual and Daft, I was working in biotech in Freenome, building out machine learning data infrastructure work for genomics and proteomics and methylation, all kinds of weird biological file formats. And then I worked in autonomous driving at Lyft, where I built out a lot of the same infrastructure, but then for images and LiDAR and radar, also weird file formats. And eventually kind of got very frustrated with the state of everything, and that's why we built Daft. Yeah, so maybe before I jump right into the core content of today's talk, which will be Rust and Python and how we make that work in Daft, I'm going to give you all a quick demo of Daft to give you an idea of what is Daft and how do you use something like it. So yeah, what is Daft? So first of all, it's a Python library. You pip install it just like you do any other Python library. Pip install get Daft. Under the hood, actually, a lot of the code is written in Rust. And so what we do is we precompile it, and then we release a wheel. And that's what you get when you do a pip install of get Daft. So once you have it, you can start running it. It's very simple to run. You just do, to create a data frame, you do something like daft from something, or read CSV, read Parquet, read JSON, read Iceberg, all of these different storage backends. I'm actually going to use Daft to just glob a path, right, in S3, which is cloud storage. It's just going to give me a bunch of URLs and the sizes of these files. So Daft is kind of made to be very multimodal, and you'll see that in a bit. And these are actually all image files, right? So we actually built an extremely optimized version of globbing to give you extremely fast globs. We love fast operations in Daft. But yeah, so now we have a data frame. You can think of a data frame as just rows and columns, right? It's just a table. Each column has a type. So this column path has a string type. And then this column is an int type. This is the size in bytes of these files. And yeah, you can expect Daft to be able to handle your usual, whoops, I haven't ran my code. But you can expect Daft to be able to handle all these usual data framing operations like filters, right? So you can do a df.where. This is filtering for rows where the size is smaller than a certain amount. And you run it with like .show. And under the hood, all this code is actually running in Rust, right? So although the API is in Python, I think the crucial part of it is that all the execution happens in Rust, which is, gives us kind of the best of both worlds. And like I mentioned, Daft is kind of built for multimodal data, complex data types. And so you can do things like, hey, that URL column, can you do a .url.download, right? In Python, you say, Daft, please URL download this thing. And then Daft will give you a new column that's just binary. And then you can also say, Daft, that column called data, please do an image decode, and then bam, you get like images, right? And these are all native types in Daft, and we represent these types in Rust as well for extreme processing efficiency and also memory stability. And I guess the other thing is that Daft is distributed, so everything can run on your laptop. That's what the demo is running on right now. But if you need to, say, scale up to 1 million images or 10 million images, or you have giant tables of like billions of rows, then you can actually scale Daft up in the cloud on the backend infrastructure called Ray. And that's very simple. You just do one line command, and you're kind of good to go as long as you have a cluster running. Yeah, that's kind of it. There's other things too. There's a query optimizations that we run to make your query even more efficient. Yeah, that's kind of like the big picture of Daft. And if you've been wondering what's all this buzz about, like data frames and why is pandas not enough, this is one of the reasons why there's a lot of innovation happening here in the data frame land. Okay, so what are these libraries used for, right? So when we think of even in scientific computing, when I worked with researchers and scientists, it all kind of looks like this, where you have your storage layer and then your compute layer, right? So on the storage layer, in industry we'll call this the data lake, right? You have storage, whether that's in AWS S3, Cloudflare R2, these are object storage, or you might be familiar with Ceph, Lustre, distributed file systems. That's where you store your data. And then you have a file format, most often something like Parquet, CSV, or JSON. You might also have a smattering of data in like JPEG, TIFFs, MPZs, protobufs, what have you, JSONs just like lying around. And then if you're not familiar with this layer, there's also a layer called the table format, which is an additional layer on top of the file format that gives you metadata about each file. But at the end of the day, you have this kind of data lake that you need to do work on, right? So whether that's doing scientific work or doing data engineering work or you're doing analytics at a big company. And then you have, I would argue, 3 main functions on your data. You would have data engineering. That's like, given X my data set, can I run something on it and then produce a new data set, X prime, right? And often that feeds something like analytics, where given a data set X, can I plot that, show a dashboard, present my results? And the third thing you might want to do with your data is machine learning and AI, right? You might want to start training models. You run a training function on your data, and you get a model. And there are plenty of data engines out there. I've just introduced Daft. There's obviously Pandas is also really good for this. You have the new entrants, I guess, DuckDB, Polars, and then you also have these other larger engines like PySpark, Dask, and Trino. And each of them are good at some things and not that great at other things, and have their own characteristics. But basically, this is what you want to do. And yeah, so Daft has certain characteristics that make it good for certain workloads. So we do analytics, we do data engineering really well, and we handle really, really large scales of compute at 300 terabytes and above. That's actually our largest use case right now. And then we are running multimodal data. OK, so that was it for the introduction to data engines as a whole. Now let me try to motivate why Python is important here, right? If you look at the big data landscape, this is me Googling big data frameworks on Google. If you count all of these frameworks, the one thing they have in common is that they're mostly JVM-based. Because all these big companies, they built the software for the big data centers, and they all built it in Java and Scala. They love that. But yeah, interestingly enough, though, this is a quote from one of the co-founders at Databricks. They wrote Spark, and they maintain it, and that's kind of their project, right? But he says, probably about 80% of the Spark users use Python. Isn't that interesting that all these technologies were built in the JVM, but like most of the usage is in Python? And here's my hypothesis, is that these engines mostly operate using SQL, the query language. And SQL is really good at analytics and some data engineering. But Python is really the language that can straddle everything, right? It can do analytics, data engineering, and the machine learning part of it too, which is where it really shines. And that's why people really like Python. The problem is, the JVM, some people say it's slow. Inherently, it's not slow. But it's just the JVM and the Python story gets really, really messy. So this is the diagram of Spark's support for Python. Everything in green here is the Spark worker. It's like literally a process running on your machine. And then it has to talk to these Python processes through like a Unix domain socket, right? It has to like talk to Python through a file. And you have in order to run any job, you're spinning up all of these workers on your machine. And it's really, really messy. And the problem is, you get like really weird error messages because sometimes connections fail. You get horrible overheads, right? It has to serialize and deserialize data between these processes. It's not built for the cloud. It's just really painful as a Python developer to work with it. So, we've established developers love Python as an interface. Spark's JVM engine doesn't really work very well with Python. You have to go through all these hoops. So, why don't we just throw Rust at it, right? It should work. And yeah, so I'm going to try to convince you that, yes, you can have your cake, you can eat it too. Rust and Python are very, very well suited for each other. We're going to do a little bit of a code dive later to show you what that looks like. And it's very easy to adopt it incrementally in your workflow. And data frames actually, Daft and Polars, which are both Rust-based, make it very easy to do that. So here are the requirements that we want, right? We want an interactive user experience that's given to you by Python. We want access to the rich machine learning, AI, and data ecosystem in Python. You have PyTorch, you have NumPy, all the really, really good stuff in SciPy that you have access to. But then Rust gives you maximize your resource utilization, right? We get to use all our CPUs. If you have really large I/O volumes, like we do at Daft, where you have to read terabytes of images, you can use Rust to do that really efficiently. And last of all, you can do very memory efficient things by representing your data in Rust, but then exposing it into Python. It's like a Python object. OK, let's do a deep dive into the demo. So, all right, this will be a fairly technical demo. I'm going to try to go a little bit slower. But first, let's prepare some data. A lot of the demo is actually just motivated from the quick start of Py03, which is the Rust bindings for Python. But we're going to do a pretty deep dive into what's going on under the hood to help you understand how you can integrate Rust into your applications and what kind of integration you actually want, right? So I'm going to go ahead and clear everything and rerun this. So first, let's create some fake data. We're just going to call it the data variable. This is what that data looks like. It's a whole bunch of J's, and Sam, and Max, right? And it looks like this. It's just a giant string with many, many rows, randomly generated, with a certain number of J's per row. And the task today we're going to try to do is to just count how many J's are there in this entire string and try to make that go as fast as possible. So let's try doing that. First, let's try a very naive Python-based algorithm, right? We're just going to keep track of the total count. We're going to iterate through each string line by line, right? This is going to produce a Python string for every line. And then we're going to count every word in that string, in that line, and just add to the total, right? Extremely naive. Let's see how this goes. So we're going to time it. We're going to run it. It will take about 6 seconds. I mean, it is a fairly large workload. There's like 50 million, J's in there. But yeah, like, this seems really slow, and it should, right? So why is this slow? This is slow because every time we do a loop here, we're creating a new Python string. And that's extremely heavy. Python strings are very, very expensive to create and loop over. And all of this is just looping over these Python objects. There's millions of these being created. That's why it's slow, right? And so at this point, you go like, oh, Python is slow. You should just totally use Rust, right? But the counter example here is if I do data.count, right? Guess how fast this is going to run? This is in 500 milliseconds. This is just pure what you would think of as Python. But why is it so fast then, right? Because actually, in the standard library, all these operations aren't just implemented in Python, right? If you dig into the .count method, it's actually implemented in C, in the CPython implementation, right? So if you look into it, it's just like this heavily optimized C code that will go through that string and look for all occurrences of the word J. So this is, I think, the counterexample as to why you should move to Rust, right? Actually, there's a ton of really, really good tools already in Python that have been heavily optimized for you. Rust isn't this like special magic sauce that you can throw on the problem and automatically makes it go faster. Plenty of developers have put in so much time and effort into making Python really performant and giving you really powerful standard library tools, right? That being said, I actually did make it go faster than 500 milliseconds using Rust, so we'll keep going, and I'll show you how easy that is, right? So let's try using Rust instead and see how easy that is to do. So the first thing we're going to do is in our Rust code, I'm going to define a count line method. It looks, if you squint, it looks very much like the Python method we had from before. We have a total count, and then for this line, we'll just iterate through the line and just count if I see the word J, essentially. And we're going to define a very naive search_rs function, which will just take all of our contents, make them into lines, and then we'll map that count line function over each line iteratively, right? So there's no parallelization, no fancy multi-threading going on here. It's just Rust taking in a string from Python and then going through each line and doing the count. So this is kind of a diagram. I'm going to build on this diagram, but this is what it looks like. You have one thread. It's a Python main thread. It's going to hold on to the GIL. Folks familiar with the GIL? Hands up if you've never heard of the GIL. OK, there are some. So in Python, every time you run a line of Python, you have to grab this thing called the GIL. It's like when you hold the GIL, you can tell everyone else, I can run the Python code now, and you cannot, right? And so if there were multiple people trying to run Python code at the same time in a single process, they will all compete for the GIL. In this case, we only have one thread, and that's why no one is competing for the GIL. This one thread is just going to grab the GIL. It's always holding on to it, and then it's going to run some Rust code. So let's run this and see how long it takes. So remember, the Python version of this ran in 6 seconds. This one is going to take about 1 second. Not too bad, right? 6x improvement just by naively porting the algorithm over into Rust. Why is this? That's because mostly, I would argue, because we no longer have all these Python strings flying around, and the Python strings are extremely expensive, right? Okay, not bad. How can we go even faster? So, why is string.count, the Python string.count, so fast, right? There's probably many reasons why. I haven't really dug into it. But one easy way we can try to beat it is to just make use of parallelization, right? The magic of doing many things in parallel. So we're going to use the excellent crate in Rust called Rayon. And literally all we do is, from before we had contents.lines.map. Now we just do contents.powerlines, which stands for parallel lines. And magically, Rust is going to run this on multiple threads for us. And magically, things are going to be faster. So this is the new search rs multi-threaded function that we exposed from Rust into Python. And I just import it here from word count, import the new kind of Rust function, and I'm running it. And there we go. We've actually beat string.count. And there was, 4 lines of code in Rust, right? So Rust gives you all these really powerful primitives to do parallelization and all that. And it's extremely easy to expose it into Python. You just kind of wrap it with the pyo3 PyFunction macro. And then all of a sudden, you can kind of import it in Python. And you have this extremely simple, extremely modular piece of code you can now use anywhere in the code base. And it's actually already a lot faster than what you might have. Cool. So, we now have a 2x speed up versus string count using Rust multi-threading. This is what that looks like. Okay, so here's where it gets a little bit technical, right? So your Rust main thread is still holding on to the GIL. The difference is that now when I call this search rs multi-threaded function, it's going to be under the hood spinning up multiple threads using this parlines method, right? So it looks like this. You have these Rust threads being spun up. The Rust threads are running Rust code, and so they don't hold on to the GIL. And so that's why it's so fast, because all these Rust threads, they're like, oh, I don't hold on to the GIL. I'm just going to run independently of everyone else, right? I'm going to do my own thing and return my own results. That's why it's so fast, and it's also sharing the string memory from Python. Now, the problem with this approach is that you kind of have to build your application around Rust. Like Rust now handles multi-threading and kind of figuring out the structure of application. What if you were actually building within a Python application, right? What if you were building a web server? A web server has its own concepts of threading, right? What if you're building your own Python application that does its own multiprocessing and multi-threading? How should you think about it then? So the problem is, let's try using Python threads, right? The problem with Python threads is that anytime a Python thread wakes up and makes a Python call, it has to grab the GIL. It looks like this, right? These are the Python threads. Every time it wakes up, it's going to hold on to the GIL, and then no other thread can run, right? So if we naively try to use Python multi-threading like this, I'm going to create a thread pool with 8 workers. And then I'm going to run our SearchPy naively and try to spread out the workload amongst 8 chunks. It's actually going to be slower than our 6 seconds initially. And we're going to let this run for a little bit. Yeah, it's slower because all of a sudden now all these threads are competing for the same resource, which is that lock. They can't run in parallel, right? So you might say, okay, so throw Rust at it. Rust is supposed to run independently of the GIL, right? Unfortunately, if you run our naive search algorithm in parallel, it doesn't get much faster than when we ran the search algorithm without multi-threading. Why is that? That's because every time you run this algorithm, the Python threads are going to hold on to the GIL, and they're not going to let go unless you tell it to let go, right? It's still holding on to the GIL even though the Rust code is running. And so the last thing we need to do is just simply call this little function right here, py.allowThreads, and now, voila, we will have extremely fast execution using Python threads, which is just about 200 milliseconds, which is what we have from before. The main difference here is that every time these Python threads wake up, the first thing they do is they go into Rust and they call this py.allowThreads and they drop the GIL. So actually, your Python threads suddenly became extremely useful, right? Because the advice you usually get is Python threads are not meant for compute-bound workloads. But now if you use Rust, or actually, honestly, if you use C++, you drop the GIL, and then you're kind of good to go. So yeah, that was a little bit of a demo of like why Rust is causing so much waves in Python. And honestly, I think a lot of the popularity of Rust can be attributed to these Python bindings. Like it's so simple to just bind some Rust code into Python, but just annotating it with this PyFunction macro, and all of a sudden you can now call these extremely powerful methods from Python and make use of them simply by just dropping the GIL. Okay, so that was a little bit of the demo. Some conclusions from me, right? So yeah, I think think very hard before you adopt Rust. As you can see, it's not a magic pill. There are a lot of considerations you have to make when you do try to adopt something like Rust. What kind of application are you, right? Are you a Rust application that intends to have Python bindings? Like, are you a Rust team that's going to be building a service that other Python developers can use? In that case, I would argue that you take the approach of doing Rust parallelization primitives and they expose a very thin Python layer on top of it, right? That was our first approach, which was extremely simple in Rust land, and then a very thin Python layer, which was just a Python function that someone else can call. The second type of application is, hey, like if you are a Python application, right? If you're like a web server or something, then I think the approach here should be to incrementally adopt Rust in places that are resource intensive, places that may be I/O bound, compute bound, or extremely memory hungry, and you just optimize that small bit of code by having this extremely narrow waist that calls Rust. The third kind of application, I'm a Python-only developer. I don't know anything about this, right? There actually are a lot of Python packages that already wrap these native code for you. NumPy is a great example of that. NumPy doesn't use Rust, but a lot of it's written in C++ and Python. And then actually, a lot of the LLM stuff today is written in Rust as well. There's a package called TickToken, which powers a lot of tokenization in LLMs and AI. And that's actually a Rust library that's exposed in Python. But to a Python developer, you just pip installing it, and then you're good to go. You're already kind of actually using Rust code under the hood. Obviously, other really good options are Polars, right, which is written in Rust, and Daft is written in Rust as well. But to you, you're just using a Python package. So I'm going to talk a little bit about like Daft because it's a fairly complicated, architecture. So the way that we use Rust in Daft is that when you're running Daft locally, what happens is we use Python to build a plan, right? So this is what the plan looks like. You call it, hey, like read some files, do a filter, and then do a join, right? Maybe. And this plan looks like this. It's actually a Rust data structure. Then all we do is we just drop the GIL and then execute the plan. Extremely simple. So locally, it looks a lot like a Rust application with a thin Python layer. When we go distributed, right, when you want to run us on multiple machines, it's a little bit more complicated. First, we build the plan. We break the plan up into tasks in Python, and then we schedule these tasks using Ray, which is a Python library, right? And then once that happens, then it goes into Rustland. Then we just drop the GIL, and we just run the task. So this is just slightly more complicated because we have to navigate this kind of distributed computing, which actually Python has a lot of really good abstractions for and frameworks for, and that's why we do that. And from a query engine perspective, what's expensive when you run a big query, right? So the first thing that's expensive is reading data, and that's what we use Rust to speed it up. How do you read CSVs? How do you read Parquet? And how do you read JSON extremely quickly at super high speeds? And then the second thing that's really expensive is how do you move data around within your system in a stable and efficient way? And so Rust gives you a lot of memory stability there. You can reuse memory and have very low-level control around memory. And the third thing that's really expensive in a query engine is how do you execute operations with low memory overhead and a really efficient CPU usage, right? That's also really suitable for Rust. And these are the three main areas within our application that use Rust. But really, you can think of it as everything is mostly in Python. And that's it. So I wanted to just plug it also. We are hiring if you are interested in high-performance systems, being extremely efficient with memory. Come talk to us. And yeah, that's the talk. Thank you.
Thanks so much. Any questions? Yes, I see one hand up there.
Hi, I really liked your explanation of GIL like that. I never really thought about it like that. That's a nice way to think about it. But I don't know the intricacies of it, but in Python 3.13, there's an option to disable the GIL, right? Does that change how you would give the talk or anything going forward?
That's a great question. So I read a little bit into it a while ago, and it seems that it might help a lot in the future when libraries such as NumPy will start adopting this functionality. But right now, actually, I believe that most of the functionality is gated behind these libraries adopting the new kind of GIL-less execution. So today, if you use 3.13, you don't automatically get the benefit of it. But once libraries start adopting it, and maybe in future versions, you'll start to see the benefits of that. And you might be able to use Python multithreading and just automatically not have to think about the GIL.
More questions?
Okay, so someone in the back corner can ask the next question. So you said earlier that in Daft you kind of build this plan. So that is, I guess, is similar to the kind of futures things and so on. How does Daft know when to start the computation, or does it start it right away? I'm a little confused as how you go from the Python lines that build that plan into scheduling the execution.
Yeah, that's a great question. So you might be thinking of it from a Dask point of view, where Dask's plans are, I think, mostly futures, if I'm not wrong. The Daft plan is actually just a data structure in memory that says a simple plan is maybe read some data, filter the data, and then run a transformation on the data, a projection, right? And so none of this gets executed until you tell it what to do. So at the end, you could say, write all this data out to a Parquet file, or you could say, show me 3 rows of the data. And using that kind of execution context, Daft then understands what you want to do with that plan and can do a lot of optimizations. For example, if you only wanted to show 3 rows, Daft will automatically insert in limits, right? So it will go in all the way down to the bottom of the plan. It will only read 3 rows from your CSV and then kind of propagate the rest of the plan. So yeah, the execution is kind of, this is called lazy execution, and Daft is lazy execution by default. The way it works is that you have a plan builder, and you ship the plan over to Daft, and you tell it what you want to execute. Yeah. Oh, I guess also to note that it feels like most engines are going to move in this direction. I know Polars by default is still eager, I think, but they have a lazy API. And that's really the only way that engines are able to get really good performance, because we can then do a lot of query optimizations and prune out data that we don't need to read.
Any more questions? Am I missing some hands? Do we have any questions in the Slack? Yes? Okay, there's apparently a question in the Slack that says, would you please tell us about the platoon of tanks?
Oh, oh goodness. Where did they find out about that? So yeah, I'm from Singapore, and I used to be in the Singapore military, because it's mandatory military service in Singapore. So yeah, I used to be a tank commander, and a platoon of tanks is 4 tanks. Yeah, I used to command a platoon of tanks. It was a lot of fun for 2 years. We don't have active military deployment, so it wasn't dangerous. But yeah, was quite the experience.
All right. Okay, if there's no more questions. Oh, there's one.
Yeah, my one question is, when comparing when comparing performance to like polars, for instance, like how do you is that sort of your what's the word? Is that your litmus test on whether or not you're doing what you need to, understanding that polars also leverages Rust,
Yeah.
right?
Yeah, no, 100%. That's a great question. People often ask me, oh, why are you building another data frame library, right? There's so many out there, and like Polars is like kind of doing a really good job. In my point of view, so the main difference between us and Polars is that number one, we are distributed, and Polars is local, right? And that's not a bad thing for Polars. It actually means that we're used for different things. Polars is really, really good at handling things that run on your laptop and data analysis that runs on a single machine. For that iterative kind of feel, which if I go back to my slides, is really good at this pillar of analytics, right? And also for some ML AI, where you just do a little bit of pre-processing. But in the wild, when you have petabytes of data and with all these images and unstructured data, and you're doing more data engineering work before you even get to analytics, that's where you probably want to use something like Daft. And so I actually view us more in competition with a framework like PySpark or Dask, which also allows you to run distributed computation. And there, the main thing that we need to optimize for isn't always just speed. Yes, throughput is extremely important, but also mostly around memory stability. Because a lot of the problems you have in the distributed computation world is things go out of memory, and they go boom, right? So that's kind of my take on it. Of course, there are some nuances. Like we try to focus on multimodal use cases, like images, like I showed from before. That's because we think that the main problem in distributed computing is that we don't account for these memory inflations as much. And so a string is a lot smaller than an image, right? And that's where a lot of problems tend to come in when we try to do distributed computing. And so yeah, I think Daft is pretty well uniquely positioned around data engineering. If you are just running everything on a single laptop, I think Pandas is great. Polars is great. And I actually think Pandas with Arrow is going to be really, really good in a few years. So, yeah.
All right, we're already 2 minutes over into the 20-minute break. Thanks again, Jay.
Thank you.
And see you after the break.